Hello and welcome to York Observatory's live Teletube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alumni Carswell Observatory located at York University in Toronto, Ontario, Canada. York YouTube broadcasts every Wednesday night at 7:30 p.m. local Toronto time. For any questions or comments you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Twitter or Instagram with the handle @York Observatory and Facebook at Alumni Carswell Ops. Good evening, everyone. I'm Maheen, and I'll be one of your hosts this evening along with Dr. Hyde, Arfa, Dhyan, and Sergiy. We also have a special guest, Dr. López-Sánchez, joined us tonight, who we will introduce in a bit. Before we get started with our show, it is important to mention that the observatory at York campus is in Toronto, and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many indigenous nations. The area is known as Toronto has been taken care by the Anishinaabe Nation, the Haudenosaunee Confederacy, and the Huron-Wendat, the Métis, and the Métis. It is now home to many indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation, our stargazing and astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. Before we get started with our main show, we want to give you a little update on some of the things you can see this coming week. Tonight, we have Capella, Pleiades, and Uranus visible. Capella is the brightest star in the constellation Auriga. It is also the sixth brightest star in the night sky, making it easier to spot. Pleiades, also known as the Seven Sisters, is an open star cluster. Tonight, the moon's monthly appearance with the bright gas giant planets Jupiter and Saturn will kick off. Wait until it's dark enough to see Saturn with your unaided eyes. After 7 p.m., Jupiter will be shining off to the upper left of Moon and Saturn all evening. Moon is currently in the waxing gibbous phase with an illumination of 58.3%. We also have the Orionid's meteor shower this month, which will peak on October 21st pre-dawn. Speaking of the Orionid's meteor shower, an amazing in-person event at the Alumni Carswell Observatory is coming up that you do not want to miss. For any updates, you can always see our website at observatory.info.yorku.ca. We will post new updates every day. And first clear night, we will run our event on the York University campus on the atrium parking garage roof. I will now hand it over to Dr. Hyde to introduce our guest speaker.
Thank you very much, Maheen. That was a wonderful update. Of course, if your skies are clear, I definitely encourage you to go and look up. And I am just super happy to be here today to introduce one of my very, very favorite speakers, Dr. Ángel López-Sánchez. I cannot say enough good things about him, but I will try to limit my introduction to the usual short blurb here so we can get started. Dr. Ángel López-Sánchez, I have a spoiler, I suppose disclaimer, I have known him for a while, and he's a very accomplished astronomer who actually completed his PhD at the Instituto de Astrofísica de Canarias in Spain, which is a very famous institute. If you ever get a chance to go there, I highly recommend it. That was back in 2006, and in 2007, he moved to Australia and started doing amazing things with the skies there, and he's been doing wonderful, wonderful work for quite a while now in galaxies, on science communication. You may have seen him on Twitter, El Lobo Rayado, which you might be hearing about later on tonight, I gather. He's also, luckily for us, on tonight as kind of our very own Hitchhiker's Guide to the Galaxies. He studies nearby galaxies. He uses the adorably named Koala instrument at the in Australia at the AIT. We don't have to worry too much about necessarily getting lost in space here. wandering through the galaxies. He is an expert, and I have no doubt he will lead us on a quest to remember. So thank you very much, Angel. I'm going to go ahead and invite you to please join us here and seal the screen share and take it away.
Well, thank you very much, Elaine, and everyone at the Observatory for the invitation, for giving this talk. I'm very happy to be with all of you, and also thank you very much for all those very nice words about me. Let me share the screen just to start my presentation with you. There it goes, that is here, and then I just need to click here, if that wants to go. There we go. Yeah, so today I'm going to be talking a bit about my main research topic here in Australia, but also from a bit more broad overview about how we astrophysicists do research and studies in galaxies, particularly in galaxy evolution. The title of the talk is Dissecting Nearby Galaxies from Australia. And I currently work at the Australian Astronomical Optics and the Department of Physics and Astronomy at Macquarie University. So we are going to be talking mainly from many observations that we have been conducting with the 3.9 meters Anglo-Australian telescope at Silent Spring Observatory. I have been working in this amazing telescope for, well, 11 years so far, I think, something like that. And yes, it is the largest optical telescope in Australia, and it was one of the largest telescopes, well, particularly the largest optical telescopes in the Southern Hemisphere, till the large telescopes in Chile were built in the 80s. And that it is. So the main structure of the 3.9 meters Anglo-Australian telescope will be the mirror that is here, hidden in that place there, just to give you a perspective of how big this place is. Have a look to this little chair in this area, or just the letters, just for accessing the technician that have to. I have never used them, but to access for doing something. So it is a very special place that I love to be working there. So I'm not only doing my own research using this telescope and many other facilities, but I also provide instrumentation support and observational support to astronomers from all around the world that are coming to the Anglo-Australian telescope to observe, or sometimes doing it remote, as we have been doing it for the last 8-9 years, and particularly during the last year and a half. But as I said, I also, my institution, it is the Australian Astronomical Optics, and the main aim for the AIO, it is development of new instrumentation technologies, software, and data analysis tool for large class telescopes. So actually a good part of my work at the moment, it is to be involved for very heavily instrumentation work and with telescopes all around the world, including the Chile, including also the AIT, and also in the Canary Islands and Hawaii and so on, because we are providing the key thing that we need. So for a telescope, we don't only need the big mirror or the big collecting area for getting your photons from the space, but you also need a very sophisticated instrument like this one to the Earth, that I will tell you a bit more about that later, in order that we can get that light and analyze the light that we get from space. But let's go to start just having a look to the sky and to the beautiful sky, particularly in the Southern Hemisphere. I have told this history many times, but believe me that being born in the Northern Hemisphere, when I finally had the chance to come to the Southern Hemisphere and look at the sky in a dark place without any light pollution around, no moon, and you see this beautiful band of stars that is our Milky Way, with the center of the Milky Way just in the zenith, is just one of the best views I have ever had. And actually, sometimes I said that it is the best view I have ever had, even considering all the views that I have had with professional telescopes, including the largest optical telescopes in the world, or using amateur telescopes because I also do plenty of amateur astronomy. That is an image that I got a couple of years ago from the Atacama Desert, just using a DSLR and combining some few images, 29 images, 30 seconds. And it is giving you the depth of the different colors and the different structures that we see in the sky, particularly in the southern hemisphere. As I said, you can get these very nice images from the southern hemisphere that you see the Milky Way, the center of the Milky Way in the constellation of Sagittarius and Scorpio and a bit of Scutum, very close to the zenith, as this image that I obtained combining something like 30 independent frames taken in all the directions to recreate this all-sky view of the sky over the Silent Spring Observatory. That is the Sky Mapper telescope. And you see plenty of things here. Also the Magellanic Clouds, which are the two dwarf galaxies around the Milky Way, part of our system in some way, and Venus and Jupiter here and there. And you still see the summer triangle in this region here. So that is Altair, Vega, and the Neve. You see plenty of things. You can imagine that in the same way that we can get these beautiful, nice images of the sky, we can try to put all the sky in just a single map, as we do with the Earth, that we have a map with all the continents or all the oceans of the Earth. Well, that will be something like this if we do that with all the sky, combining images from the northern hemisphere, majoritarily coming from that part, and the southern hemisphere, majoritarily coming from this region here. And the center of the Milky Way, it is exactly in the center of this figure, with the plane of the Milky Way exactly in the equator of this figure. And we are seeing the projection of our galaxy in the sky. And that is something that, as I said, I have tried to explain many times. It is something that when I think about that, it's just giving me the chills, because it's just amazing that we can just start to explore our galaxy and the universe just with these tools. So we can go and understand a bit better where we are located. So in this kind of structure and the center of the Milky Way and the spiral disk of our galaxy. But still, we can see the Milky Way only from inside, because we are inside of the Milky Way. However, we have been able to get a better understanding of how our galaxy is, just observing other galaxies and doing plenty of other observations within our galaxy, not only with optical telescopes, the telescope with the light that we see, but also using infrared and radio telescopes that we can explore a bit further into the distance. And now we understand much better that the center of the Milky Way, which is a very dramatic place, we have a supermassive black hole of around 40 million times the mass of the sun, and that is located at around 28,000 light years from our sun. And the Milky Way have a bar, this kind of bar, and from the bar, two very prominent spiral arms appear. And we are not too close, not too far. Actually, we are in some place around here between the two main arms, which is a very convenient place because of a combination of reasons. And there are many more things that we can say about this image, including, for example, this dwarf small galaxy in Sagittarius that is colliding also with the Milky Way and have been added in this illustration. I want to emphasize that this is an illustration, that is not a real image, that is a cartoon trying to represent what we think our Milky Way is. And we know also that because we have seen many other galaxies around there that have a similar structure. And in this point, it is when I try to emphasize how important the colors are for astronomy. And in these color images, the colors are telling us things. They're telling us, for example, where the young stars are located and where the old stars are located. Because the very young stars are usually much more luminous in blue colors, while red stars are usually very old stars that are more located in the center. And the other thing that we see here, so that will be the center of the galaxy M83, and the disk with blue stars, plenty of blue stars in M83. And the other thing that we can see here, it is all these pink regions that are star-forming regions. These are the nebula of the galaxy, as well as plenty of dark patches that are consequence of the dust, a lot of amount of dust that is located in the interstellar medium of galaxies. All these are key ingredients for understanding galaxies and galaxy evolution. So it is very interesting that in any case, even though there are trillions of galaxies out there, we can classify almost all the galaxies basically in 3, 4, sometimes even 2 categories, let's say, depending how you count. I have 4 here trying to represent a very schematic Hubble timing fork from the elliptical galaxies to the spiral galaxies, and a system that is in between that are called lenticular galaxies. Spiral galaxies such as the Milky Way of M74 or M83, as we saw before, they have plenty of star formation. They have all these pink regions showing the star formation, blue stars, plenty of gas and dust. So they are in that way active, in regardless that they have a big bar in the center or not. However, elliptical galaxies are usually just having very old stars, reddish color, very orange reddish color. They don't have a star formation. They don't have gas or stars of star formation. So they're kind of different, very different system. And usually these are much larger than the spiral galaxies, but it's showing some kind of evolution. It is funny because in the old times, so we still are referring this kind of galaxies as early type and this as late type, although Hubble himself never said that that was a kind of evolution. It was just a convention. Although now we know that if there is an evolution, that it's still some debate, it will be from spiral galaxies moving into elliptical galaxies with the proper evolution. But I'm missing here something important, that are the dwarf galaxies. So there are actually many more dwarf galaxies that standard elliptical or spiral galaxies out there in the universe. They are the most numerous kind of galaxies, and particularly they were critical at the beginning of the universe because the majority of the main entities at the beginning after the Big Bang, they were just these small entities, dwarf objects that were colliding to form larger and larger galaxies. But there are still many of these dwarf galaxies in our nearby universe, and some of them are quite interesting because when we look at them, we see that they seem to be a giant nebula. So they are all forming stars. For example, this object here, the dwarf galaxy NGC 4214, it is a beautiful starburst galaxy. So what we are seeing here is the interaction between the massive stars and the stars that have been just born, for example, in that region here, with the gas, surrounding gas, that's the gas that have been forming these stars. And that allows me to introduce a bit more about the colors that we see in the universe and also how we actually do the astrophysical work that is not using images, but using spectroscopy. I mean, trying to get the light of an object and trying to analyze what features we see in the light of that object. That is a beautiful image that I got of the Eagle Nebula M16 using the INT, the Isaac Newton telescope, at the 2.5 meter telescope at La Palma Roque Muchachos Observatory in the Canary Islands, while I was finishing, after actually I finished my PhD. And it is showing in red the glowing of the gas, the H alpha, what we see, the hydrogen gas that is glowing because of the effect of the very massive stars here, particularly in the center. These stars that are in this kind of image glowing in blue, but it's just a codification of colors. So we can get one of these stars, the light of that stars, and analyze in a different way. But we can also use these images for getting a bit better understanding of the different kind of elements, chemical elements that are in the nebula. For example, this image, what it is showing is in blue, the oxygen that is highly ionized because of the center of these very massive stars, and that is in blue. And in green is still the H alpha, as it was in red before. And now in red, I'm showing the sulfur, the emission of the sulfur. That is very, very well showing the limitations and the changes in densities, the walls in the nebula. But as I said, we can get a better understanding of these features if we go into a spectroscopy, into dissecting the light. Just if we get the white light coming from a particular star, and we use a grism or some kind of other device that is able to disperse all the white colors into the rainbow colors, and we see, we put there an instrument that is able to amplify that light, and we see that it is not a continuum, that it has plenty of features, of these absorption features, that is in the case of a star. These are the chemical elements and ions and molecules in that star. So even though we are not able to go physically to that star and get a bit of it, a sample of it, and analyze it in a laboratory, thanks to the analysis of the light using spectroscopy, we can know plenty of things about them. We can know the chemical composition, the main physical properties. We can even know the distances to galaxies and so on, as I will tell you a bit more. But that is for a particular star, that is for a star. If we are observing the glowing gas of a star-forming region, we have something very different. That is, we see basically not a continuum, it is just black, so there is almost no emission, but from time to time we find very particular places where we see this kind of light. These are emission lines coming from different chemical elements. For example, that one is H beta coming from hydrogen and oxygen, these two, and that is H alpha, from hydrogen. So that is going to tell us again a bit more of the properties of the gas of galaxies. Of course, we usually, when we are doing in professional astronomy, we are not using these beautiful color bars, but we are using actually plots that are showing, well, the wavelength, that is the color from the blue to the red, and the intensity of the flux in the vertical axis, showing where those particular wavelengths have plenty of emission lines, showing the different lines that I was showing you before. But how can we get the colors in astronomy? Actually, I have a nice video in YouTube that I'm not going to show here because it is 15 minutes, trying to explain all of that and why we use the different colors for getting a better understanding of the physics of nebula in particular. But let me show you at least this. We always, in astronomy, almost always, we use monochromic cameras, but we use also filters. So we are trying to get very deep. So we put a monochrome camera, and with that use filters in the V color, in the blue, in the visible, and in the red. And then we provide each of those images with a color, the blue in the V in blue, the green G in green, and the R filter in red. And we combine them and we get the physical, the color image, trying to reproduce in this combination more or less what our eyes will see. That is not all what we always do. There are other combinations. For example, for nebula, what we do, it is just using special filters. Sorry for that. We use special filters that allow to observe particular objects, particular lines of this nebula, and with that combine them into this beautiful image as I was showing you before. Let's see why I'm not seeing this going ahead. There it is, sorry. So we see, for example, a filter observing the H alpha, another filter of observing the oxygen 3 with brackets. If you want to know, ask me later. And the sulfur 2, don't forget the bracket because these are forbidden lines. That is for amateur astronomers, please don't forget the bracket. And then we put the different images, the oxygen 3, the H alpha, and the sulfur 2, and we then combine them, providing each of them a color, oxygen 3 in blue, H alpha in green, and as alpha 2 in red. And that is why we get these beautiful color images. This, for example, it is a color, a palette that is called the Hubble palette, because although the Hubble Space Telescope was not the first to use this kind of color images, it has been very popular producing this kind of images. Anyway, so coming back to galaxies, so how do we measure the distance to the galaxies? How can we get all this information from the distant galaxies to be able to understand them a bit better? Well, imagine that the light from galaxies and stars, well, particularly the galaxies, are moving in the space from sometimes million or billion years, finally arrive here to the Earth, and they are collected with the Anglo-Stanton telescope in this case. And you have seen the light moving a funny path because this the Anglo-Stanton telescope have an optical fiber complex that have around 55 meters long, and it is driving the light from the primary focus into a room that is below the telescope where the spectrograph is located. The spectrograph, it is this instrument that is able to dissect or break the white light into all the colors of the rainbow with a complex of lenses and prisms and dichroic and so on. At the end, what we want to get, it is just that to be focused on a detector. Actually, we have several detectors depending on what we are using, and in this detector we are compiling the different spectra that we are getting from different parts of the sky. And for example, in this simulation, we have on the top an object that we see plenty of these emission lines. That means that that is a galaxy that has a star formation because we see the nebula in that galaxy. However, in the bottom plot, what we don't see emission lines, but we see very prominent absorption lines in the sodium, the calcium, K and H. These are two very important, the G band and magnesium too, and even sometimes H alpha. That means that that is a galaxy mainly made of all stars, red stars. And when we get the images, well, we can confirm clearly that the top one was a star-forming galaxy and the bottom one was more an elliptical galaxy. So what astronomers have been doing for a lot of time for understanding galaxies? Well, we can go and get the spectrum of a particular galaxy and analyze the different features that we see, and then we can get the distance in a first approach using the Doppler effect, although that is not the proper distance, but the radial velocity for sure. We can estimate the relation between giant stars and other stars. We can determine the chemical composition, the age. So you have plenty of information that we can get there. And then we go and observe individually another galaxy. Of course, for getting the detail of what we need, the depth for getting something like that, we need, let's say, an hour observing, integrating the light of that particular galaxy. So if we have to go an hour, we will only be able to complete 9-10 galaxies per night, and that is not efficient. So at the AICO, we have been pioneers developing this kind of instruments that are able to do much more than that. The 2 degrees field instrument, or 2DF instrument at the Anglo-Australian telescope have been working for the last 23 years. And it is just a very powerful machine, still working very, very, very well. It has 400 optical fibers that we can allocate anywhere within this plate that you're seeing there. And that plate has a size in the sky of 4 full moons, 2 degrees. And that is why the instrument, it is called 2 degrees field. So in a good winter night, we can observe, let's say, at around 360 winter night, every night we can observe 360 galaxies. So that means in a good winter night, around 3,000 objects. We cannot put all the 400 fibers to observe galaxies because we also need fibers for observing the calibrations, the guiding stars and the sky for subtracting the background and so on. But still, it's very powerful. So in only 4 clear nights, 2DF is able to observe 10,000 galaxies. And that have been the power that have been able to create very deep maps into our universe. Not only the very first 2DF GRS 2 degrees field galaxy redshift survey that was completed in 2002 and was providing a very nice view of the large scale structure of the universe. But also, for example, this survey, the Galaxy and Mass Assembly Survey, in which I have been participating, and many of these are actually my observations, in which in 5 very particular direction of the sky, we were able to observe around 320,000 galaxies to a depth of 5 billion light years from us. And that is a simulation of using real data of one of these slides, one of these direction of the sky, in where all the distances between galaxies are real. The images are also real, coming not from the from 2D, but from the Slow and Digital Sky survey. However, for the purpose of this animation, the relationship between distances and the sizes of the galaxies have been exaggerated. So the galaxies are actually much more smaller than what you are seeing here in this scale. But if we try to be accurate, the size of the galaxies will be much more smaller than the pixel size for this animation. So there was a compromise that we have to get. Still, when we have a galaxy such this one, the M51, the Whirlpool galaxy, that's a fantastic image obtained with the 1-2 meters Calar Alto telescope in southern Spain, in Almeria. What is representative of the galaxy? So we have been talking so far about this spectroscopy, but using just a particular part of a galaxy. What is the representative? That part, the center, another region, this companion. So in the last decade or so, actually a bit more than a decade, for almost 15 years already, we have been developing this kind of new instrumentation that is called integral field units for doing integral field spectroscopy. That is getting for a particular object, not one spectrum, but hundreds of thousands of different spectra in order that we can create what we call a data cube. So for a particular object, we are going to have this data cube in which in 2 directions, we will have the image, if we scroll in this direction here, and the 3rd direction will be the spectrum of that particular pixel or the different region of the galaxy. And that is very powerful. So again, it was here at the Anglo-Australian telescope when in 2012, 2011, 2012, and starting officially in 2013, we created this amazing instrument that is called SAMI, that stands for Sydney AIO Multi-Eye View Survey. And it is just a little, so it has 13 galaxies that we can observe at the same time using this kind of a special optical fiber that we call hexabundle. So this optical fiber, it is not only one optical fiber, but a bundle of 61 different cores, and we can dissect 13 galaxies at the same time. So we've got more than 3,000 galaxies between 2012 and 2018 as part of this survey galaxy of SAMI. By the way, I always have to say this comment. In case you don't know, the birth of the color astronomical, that's the images in color in astronomy was actually here at the Anglo-Australian telescope by David Malin in the year I was born, actually, 1976. And it is having always something that can have been quite deep for me, that later, 40 years later, I have been using the same cabin that David Malin was using for obtaining these beautiful plates that later have been in books and in posters all around the world for helping the SAMI team to dissect galaxies using this instrument. So we have plenty of these observations done, and we can get different, we can understand much better the galaxies using this kind of technique, because the analysis of these features allows us also to see movements. For example, that is a galaxy, and depending on where we are, we can estimate how the galaxy is rotating, just using the different features where we see them and that are changing because of Doppler effect, because of the rotation of the galaxy. And that is something very powerful. Right now, the next step will be, or it's going to be Hector, that is with this kind of instrument that are going to be moving around, and that will be for late 2021, beginning of 2022. We are going to be dissecting even more galaxies. But at the end, understanding galaxy evolution, it is quite complex because there are many things that we have to take into account, from how the gas is condensing in galaxies, forming these interstellar clouds that are condensing even more from molecular clouds, and we have star formation, and stars themselves are evolving and interacting with the galaxy. But all these kind of surveys that we are conducting right now, they're usually trying to dissect only big galaxies. But that have a problem. So these are galaxies that usually are not small, they are not dwarf, and they are too far away for being very well reserved. And we also cannot get deep into the very emission lines that we can see in these objects, in order that we can get a better understanding of particularly the chemical composition and what we call the metallicity. And on top of that, we are not able to avoid completeness with what we call the other wavelength, with radio in particular, but also with infrared. So they don't have these kind of observations. So imagine that when we can get one of these star-forming regions with detail, we have not only 2 or 3, we have tens of emission lines, and some of them actually are very important if we want to understand the chemical properties of the interstellar medium of these galaxies. And we need all that information for understanding better how galaxies are evolving. And as I said, and particularly understanding what we call the metallicity of the metals, because in astronomy, probably you know the joke that for us astronomers are very easy in regarding chemical composition. We say these objects have hydrogen, helium, and metals. So everything that is not hydrogen and helium, it is a metal. We usually are tracing metals with the oxygen or with the iron, but they're very important because metal is a way of measuring how much the gas have been processed into stars. Imagine that at the beginning of the universe, only the hydrogen and a bit of helium were created. All the rest of the chemical elements have been created because of the stellar evolution, cooked in the stellar interiors, or because of the action of the stars when they are dying in supernova explosion of neutron star mergers or something like that. So that is very important for getting the understanding the chemical evolution of the universe. So we need also that information. Metals are also tracing infalling of pristine gas that we see that the gas doesn't have too much of these metals or outflows, and many other things. And at the end, if we want, for example, to understand how planets have been able to form, or how even life have been able to form, we need to get all these little pieces with the metals. And on top of that, as I was mentioning, we need also the other colors. For example, one very important, it is hydrogen, the cold hydrogen gas. And for this one, what we have here another nice image of M83 with some ultraviolet observations that you see here on the blue. The real reason I moved to Australia 14 years ago was for starting to participate in a survey for observing in gas using radio telescopes nearby galaxies, and we got something like that. So in M83, that is a very famous galaxy, and many of you perhaps have seen it using an amateur telescope. Think about that if we were able to see this with radio glasses, that galaxy will be almost a degree in the sky because of all the large amount of neutral gas, diffuse gas that we can see there. And it is also the best way of tracing galaxy iterations. So as I said, I moved to Australia precisely to observe many of these dwarf galaxies. But coming back to the Anglo-Australian telescope, we have here one instrument that is called Koala, that it is one of these integral field units for which we can use for dissecting galaxies. So my main research project during the last few years have been conducting observations using this instrument that I'm also the instrument scientist. for what we call the HiKids project, the H1 Koala IFS Dwarf Galaxy Survey, that is exploring something that is not currently observed with the surveys that have been conducted using IFU, because we are tracing nearby dwarf galaxies that are H1 rich, that have plenty of gas, and for which we already have these radio maps showing the distribution of the neutral gas around the galaxy. I'm quickly going to show you some 2 or 3 results, and with that I'm going to finish that. Imagine that for this we have one of these galaxies, POC4, with plenty of these emission lines, and some of them are critical in order that we can determine much better the chemical composition of these objects. So that is quite good. And we can also trace how that is moving, how the gas is moving. You can see that in that animation. And for example, in this object that is the center of the blue, one of these dwarf galaxies, if we analyze the chemical composition here in the brightest part in the center where this blue circle is, compared with that other, the red one, we see that the chemical composition is quite different. And this dwarf galaxy, it is even the dwarf object here, that is a dwarf galaxy, the dwarf object is even less chemically evolved than the main object. And we're quite sure that that was an independent object that crossed across this main dwarf galaxy, and that triggered the strong star formation event. And another of my favorite objects, it is 1230, this kind of galaxy here, that have 2 very prominent star forming regions into part of the galaxy. Let me show you in a different way. So that is still the same galaxy. That is a foreground object that is closest to Earth, that this one. When we observe this galaxy with the radio telescopes, we can see the distribution of the gas, of the diffuse gas, that is showing this kind of tails, and even another independent object here that no one knew about it, that is an even smaller object that now we know that is another dwarf galaxy with star formation that interacted with 1230 and triggered the star formation there. So we are still in very exploratory spaces here, because actually, and I have not said almost anything, but the majority of my work in the last 3 years, besides getting observations, and we have already completed observation of around 72 dwarf galaxies, have been processing the data, plenty of software development and software processing, and still getting there. So probably, and I really hope that perhaps in a couple of years I will be able to show you much nicer results from all these amazing data set that we are obtaining, but are very, very promising. And I think that I have been taking a lot of your time already. I have given you this kind of overview. So thank you very much for your time, and I will be ready for getting questions.
Well, thank you as well, Angel. It's been absolutely wonderful to have you here, as always. So it's it's always wonderful to see the images that you're able to produce. We do have all kinds of questions and various things happening. I'll just give one real quick question over from chat. You did say you've got a huge variety of galaxies and different surveys that you've looked at, and I'm going to adapt this a little bit. What's the most distant galaxy that you've managed to image?
Well, actually, I have been observing galaxies also as I show, for the Gamma team, and these have been observed till almost 5 billion light years away. Although particularly I have a bit of a special connection to a project that we conducted under the Australian telescope in 2018, when we have Professor Brian Cox doing a live TV broadcast here in Australia, and we had a program of citizen science for detecting a supernova in other galaxies, comparing different images, taking some few weeks, and then around that the moment that we released that, and just several citizen scientists noticed one object, and I was at that time also scheduled for doing my observation of dwarf galaxies with Koala and the Anglo-Australian telescope. And we pointed to this target that was around 1 billion light years away to confirm with this instrument that using Koala, and that was actually a supernova, and a type 1a supernova. So now I can say, thanks to that experiment that was successful for several nights, that I have published 2 research papers with Brian Cox. So it's quite interesting.
That's wonderful. And just to remind everyone who is watching, can you believe our speaker also does all this amazing outreach in his extra time as well? So we're incredibly, incredibly lucky to have you here, being so busy. And since we've got you, though, we do have a couple questions from our intrepid crew. So I'm going to hand you off to Arfa, who has our first set of official speakers questions. Take it away, Arfa.
Thank you so much, Dr. Hyde. And thank you so much for such an amazing presentation. And I got a few questions for you. So my first question is, why did you choose Wolf-Rayet galaxies for your first blog?
That is an excellent question. And believe me that sometimes I have been thinking about changing it. Anyway, let me go for it. The formal title and the final title of my PhD thesis dissertation was Massive Star Formation in Dwarf Wolf-Rayet Galaxies. So in that time, I was observing galaxies, mainly dwarf galaxies, but not only, and that were very strong star-forming galaxies. And one of the features that we see when we have a very strong starburst of star formation, it is that we still have plenty of very massive stars, including the most massive stars that we can find. These are the Wolf-Rayet stars, that are the latest stages of the more massive stars. So these kind of stars that are peeling themselves, doing a kind of a striptease, a very nice image like this one that you are showing right now, heading 2427. So I remember that I wanted to create my blog in astronomy, that was the very first blog fully dedicated to astronomy made by a Spanish astronomer in that time. I'm talking about 2002, 2003. But I remember that I spent a lot of time trying to find a funny name in Spanish. So Wolf-Rayet, it changed to kind of Lobo. Wolf is Lobo. Rayet doesn't have any kind of translation, but it's like lined. That it means rayado. So the Wolf-Rayet, Lobo-Rayado, line wolf, that have been the kind of things that I have been using in social media and in blogosphere for a lot of time. Of course, when I moved to Australia, Lobo-Rayado, being also Ángel, its pronunciation difficult for English speakers, and I remember that I tried to change it, and I still have been thinking about doing it. But there are many people that have really asked me, don't do it, because that is the way that we have known you for 20 years. So, well, I don't know, perhaps I will do something about that. But at the end, it was because I was studying this particular kind of very massive stars in dwarf galaxies, and I found that funny to do the translation into the Spanish to Lobo-Rayado.
Thank you so much. I actually have another question for you. And that is, out of all of your amazing outreach activities, which one is your favorite?
I will say that something like the one that you are showing at the moment, it is my favorite one. Being with the people, showing people the beauty of the night sky, and being with the telescope, or showing, in that case, it was a science fair during Australian National Science Week, that we are showing the different technologies that we are developing at the AICO with the optical fiber, that is the kind of the red cable that I have there, that you can conduct the light from one place to the other, and even use it for reading in several meters distance, a piece of paper and reading it in the other end of the optical fiber. That is very, very, very funny. So I will say that still my favorite outreach activity, it is everything that is involved being with the public and sharing my passion about astronomy, science, and research, and a better understanding of the world and the universe we are living in.
Wow, I mean, I 100% agree with you on that. Thank you so much. And now Dhyan has some questions for you as well.
Excellent presentation. It was very educational. And I guess my first question would be, how do you differentiate, like what makes a galaxy gas rich? Like, how do you decide which galaxies to use for your research?
Well, that is another very interesting question. And in some way that is easy, because that is going to be also driven by the star formation usually. But at the end of the day, it is if we have been able to detect using radio telescopes, if we have been able to detect the H1 gas, then we can say that it's gas rich in some way. Of course, depending on how you are talking, that is not the definition of gas rich. If you are talking about a sample of galaxies that they already have gas, they all have gas, then you can start to establish, okay, what is the limit that is doing that they are very, very, very plenty of gas. That is not the case. The case I'm discussing today, it is much more about, okay, these are galaxies that we know that they have gas, and the gas is actively in some way condensing, forming stars, and that is all the kind of system that I have been trying to analyze. And I have not been able, perhaps because I didn't want to take too much time to go into details why this connection between the gas that is condensing and the properties of that gas connecting with the stars that are forming there, and the gas that is glowing as a star forming region that have the properties of the chemical properties of the galaxy are deeply connected together, but still, although many of these relationships are not well known, just a little bit, and not even well known the physical meaning of all of that, and why these what we call scale relationships are coming from. But yes, at the end, answering again your question, if a galaxy we see that have gas detected using radio interferometer, using radio astronomy, then we say that have gas rich. And if they don't have gas, it is just gas poor. They probably will have some few gas, but we are not able to detect that gas because it is very faint.
So the researcher as a person gets to define how much gas is a galaxy gas rich, right? Like,
yes, you can see that, you can say that way. And again, it also depends on the context, because when, as I said, in this presentation in this kind of analysis, gas rich, it is everything just considering a galaxy that have been able to get gas, and it still have gas, and it is forming stars. But for other people who are doing also this kind of studies, of similar studies, they are already considering only galaxies that have gas, and then they can define gas rich in a different way. So that is happening in many things in science, not only in astronomy, that there is a particular definition that you have to put it into context of a way. You have to explain why you are saying this and not the other thing, because in the other study, there is another assumption that have been considered. So that is why your question is quite pertinent, it's quite important, in order that, well, first you can, all of you can get a clarifying of all of that, but also to see that you have to know your assumptions before starting your very own research.
Great. And one more question I had was, so on your, one second, I'm trying to, on your website, you mentioned that you're using the instrument, what was it, Koala? You're the scientist for Koala at AAT. So could you exactly how Koala works? Like, how does it collect IFS data on the gas-rich galaxies?
Yeah, for that, lend me one sec, because I think it is best if I can show you a slide that I was going to use, but at the end I didn't use because it has a bit of too much extra information, and you will see that very quickly. So you lend me one sec, I'm going to share again my screen, and then you will see what I'm talking about. So Koala, which stands for Kylo Fiber Optical AET Lensless Array, it is this kind of instrument that you see, as you showed in your image before. It is in the Cassegrain focus, and it is an array of 1,000 hexagons, each hexagon having a size that we can select, but every one have an optical fiber at the end that is feeding the spectrograph in the same way that 2DF was feeding also a same spectrograph. So you can imagine this is like a CCD detector, a special CCD detector in some way, made of, instead of pixels, square pixels, hexagons, because hexagons are also good for completely filling a plane. And each of these hexagons is going to have an individual spectrum. And in that way, we can dissect at the same time a large part of the sky. Koala also have a lens that is able to change from having a small spatial sampling, 0.7 arc seconds, and then the field of view, it is small, 14.3 arc seconds times 28.3 arc seconds, or a bit larger spatial sampling, 1.25 arc seconds, the size of in the sky of each of these spaxels, the lenses, and that will provide a field of view of 27.4 times 50.6 arc seconds. And these usually dwarf galaxies in the local volume in the nearby universe have around a size of 1 arc minute. So that means with a couple of pointings with Koala, we can cover the majority of the galaxy, sometimes even smaller, and we can only use with a pointing, as it was the example that I was using before.
Oh, okay. Yeah. Now I'm going to pass it off to Sergey. I think he has a couple of questions.
Excellent. Thank you so much. That was a wonderful presentation, Angel. I have my first question to you is, why was the Southern Hemisphere chosen to host the Hi Kids program? Would it work in the Northern Hemisphere, for example?
Yes and no. There is much that I can be saying about why. The main reason I will say it is because I was in the right place at the appropriate time. So I was working, and I have been working at the Australian telescope that have this amazing instrument, like Koala, that is able to do something like that. But at the end, what we have been also using as the H1, from Hi Kids, the H1, it is from these resolved interferometric data. And for that, many of these galaxies are actually in the southern hemisphere, because Australia have always had a very powerful tradition in radio astronomy, using not only the ATCA, the Australian Telescope Compact Array Facility, or radio interferometry right now, in combination with the Parkes radio telescope, but also now with the ASCAP, the Australian Square Kilometre Array Pathfinder, in the other part of the country, in the western coast. Actually, they are in the middle of the nothing, 2,000 kilometers north from northeast from Perth. So that was something that we already had. We already have these amazing data in radio of all those galaxies, for which we didn't know almost nothing in optical. We only knew, well, we have some images, of course, but not very deep. And something that I understood very, very soon during my PhD was, if we really wanted to understand these galaxies, we have to go deep, meaning observing them for a long time, integrating many, many times to get faint details like tails and plumes and things that we are finding in the majority of the galaxy when we are going deep enough. And they will be perfect targets for being dissected and with Koala, and using that for understanding the dwarf galaxies used in IFU, because that is a kind of a topic that have not been much explored yet. Of course, there are other IFUs around the world, and there are some few others in the Canary Islands, in Hawaii, in observatories there in the US too. There is another very powerful IFU unit, that is the Muse IFU in the 8.2 meter VLT. By the way, we have a little subsample of around 10, 12 galaxies that have been observed, but from VLT, again, Southern Hemisphere. So that was actually at the end the reason why we did that. I would love to have something like more dwarf galaxies coming from the Northern Hemisphere, but it will be something that in the future, let's say in the future. And at the end, hi kids, the K comes from the koala. So it's just the way that it appears.
Thank you so much. I have one last question. What will the future of galactic research look like, in your opinion?
Well, if you are talking galactic research about the evolution of galaxies and galaxies research in general, there is still plenty that we don't know. We have, in general, a very good idea of how things are working, but at the end, it's the same as always. In the moment that we get better observations and we get a bit more data and we go into details, some few things are not fitting as we thought that they were fitting. So perhaps you have heard also about the importance of big data in astronomy, and actually astronomy have been one of the main drivers from this thing, the big data thing, for a lot of time. Elaine can also tell you plenty of things about that. So we are just going to try to get the best of all these amazing tools and software and big data exploration and so on for understanding how galaxies are formed, how galaxies evolve, how star formation is happening, and how at the end galaxies such the Milky Way have been able to be as we see them now. That will be connected also with one of the main question of astronomy at the moment, which is what dark matter is and what dark energy is. We don't know any of that. So that is also very well connected. I'm not sure if we will get answers from the astronomical point of view or from the particle physics point of view, perhaps more for the particle physics in some aspect, but if you want, ask me later a bit more. But definitely it is changing a lot the way we do it. So the way I did research when I was a student, a PhD student, just 14 years ago, it is very different to the way PhD students and young astronomers are doing it today. And it's definitely going to change even more in 10 years. So I remember that for my PhD, I actually prepared the proposals for going to the telescopes and collect data during some few nights in different optical images, spectroscopy, near infrared, and so on, and then reduce the data, process the data, analyze the data, and so on. And that is not the case almost anymore for research for PhD students. Right now, there are large surveys, large collaborations with plenty of tens, sometimes hundreds, sometimes even thousand astronomers, as the case of the detection of gravitational waves and so on, that they are collaborating together and you are not doing everything. So you are basically exploring a big data set of observation that someone has provided using sometimes also archived from the Space Telescope and so on. And that have a good and a bad thing. A good thing in the sense that you're going to start exploring much better the intrinsic relationships between properties and galaxies, and adding the theoretical modeling and so on in those analyses for getting a more physical understanding of what is happening. But had a negative thing, in my own opinion, that is that young astronomers are losing the opportunity of going to telescopes to observe and to learn the techniques for really being in the telescope or at the telescope during several nights, collecting the data, being sure that you are getting the best of that, and then processing the data in a different way. So these are techniques that we are that perhaps it's going to be a bit lost in some way. That is why I always encourage students to try at least once try to go to an observatory and see how it is. And it is not the same thing doing it remotely. You actually have to go physically there if you really want to get the best of it. On top of that, enjoying a really good dark sky. Because I have mentioned a couple of times the problem of the light pollution in our lives and in our society, that in this time that we are talking a lot and we are trying to fight climate change, it's something that I don't understand why we don't just, take a bit of care in illuminating properly our cities and our towns and reduce electricity bills and emission of CO2 in the atmosphere. Because we are losing something that is very deeply connected into us, which is the night sky. And you can recover that in some way when you're going to these places. I don't know, for me, it is just a very personal, deep connection that I have with the night sky in that sense. And I'm sorry that I jumped from your question into thinking about other things, but was the way this conversation has been going.
Don't worry about that. That was very interesting. Thank you so much for your insightful answers.
Anytime.
All right. Well, I think we're probably going to wrap up here now. That's probably about all the questions we have time for today. So I'm just going to say thank you again to our wonderful speaker, and Angel. We do have, of course, lots more we can talk about, but maybe not this time. So thank you very, very much again. And Sergiy, it's going to be over to you to do the outro.
Well, everyone, you have been listening to Ellen I. Carswell Observatory's weekly Teletube broadcast, the Astronomy and Astrophysics program, written and presented by the students, faculty, and alumni and friends of York University. A special thanks to Ángel R. López-Sánchez for joining us tonight and giving us such an amazing talk. The hosts this evening have been Dr. Hyde, Arfa, Dhyan, Maheen, and myself, Sergiy. Make sure to leave any comments or questions in the comment section of the video and talk to us in the chat right now. All of our programs are free, but if you'd like to make a donation, see our website at observatory.info.yorku.ca.